let's start. We will hear 3 talks about oscillating dynamos in the morning, and we're starting with Giesecke from Dresden-Osendorf. Yes, please.
Yes, thank you. The title of my talk is Oscillating Alpha Square Dynamos. Essentially, I will talk about the spectrum of an dynamo operator of alpha square type. Motivation are reversals of the Earth's magnetic field, but this is only a motivation. I will not develop or explain any reversal model. So reversals of the Earth's magnetic field are abrupt transition of the dipole component from one orientation to the other. They occur since at least 3.2 billion years, irregularly, and the last reversal is about 780,000 years ago. They have similar geometry, and as far as we know, the probability of each possible polarity state, there's the same probability for both states. This figure shows the sequence of polarity states for the last 160 million years. And we see that reversals occur on very different timescales. We have here the so-called superquark, where no reversal at all occurs for nearly 40 million years. But we have also very frequent reversals in other time periods. There also exist some cryptocorns, which are consecutive reversals that occur very fast with a stable period, which is smaller than 50,000 years in between these reversals. So we have, on the other, and during the same time, higher multipoles, quadrupole, octupole, and hexadecupole are increasing for at least a short time span, and then the whole all modes together decrease, and the reversal takes place somewhere in between these time span. And after the reversal has taken place, only the dipole component is significantly increasing in energy. And we see that during the reversal itself, dipolar and quadrupolar energy are of equal magnitude, so both modes seem to contribute. And we also see that the magnetic field does not vanish completely during a reversal, so we still have some kind of field even at the reversal itself. In 3D MHD simulations of convection-driven dynamos, also reversals have been found, but only in very short periods are covered, and the parameters differ from realistic values. For example, the magnetic quantum number is in reality, is much, based on the molecular values, is much smaller than 1, whereas in the simulation it's always of the order of 1. So the small-scale magnetic field should be damped, and this leads to some models that try to describe the dynamics of the field by a small number of modes. So the most simple model would be to describe the magnetic field by interaction of, or to describe a reversal model by interaction of 2 different modes. Then you can develop a nonlinear amplitude equation that allows transition from plus B to minus B. Irregular occurring reversals have also been found in alpha square and alpha omega models with fluctuating alpha effect. This figure shows some field, or the time development of the magnetic field of an alpha square dynamo model with such fluctuations, and we have an irregular, from time to time, some reversal takes place. So the question that arises now is how can these nonlinear amplitude models and mean field can combine with mean field models? So which modes can be are interacting in such nonlinear models to describe reversal, and can they be identified in these paleomagnetic measurements? So as we have seen in the figure at the beginning of the talk, the quadrupole and dipole during a reversal are equally important, or seem to be equally important. So is it possible that these both modes are interacting? In that sense, the next question is, are such models sensible at all? So can a reversal be interpreted as a half or as a part of an oscillation And is the proximity of a stationary and oscillating state of a dynamo essential for reversal? Or is it completely different? Is there a fundamental difference between oscillating and irregular reversing dynamos? So for that reason, we will examine the mean field induction equation. We have the usual scale separation. We have the mean field induction equation where the electromotive force is expanded, and we have some source term proportional to the mean field, which describes the alpha effect, and we have some beta effect. In the simplest case of isotropic non-merosymmetric turbulence, we end up in the mean field equation for an alpha square dynamo, which looks like this. In general, the turbulence, at least in such fast rotating bodies like the Earth is strongly anisotropic, and alpha and beta should be tensors of second or third rank, but we do not regard this problem in our models here. We also do not bother about the nonlinear back reaction. We keep the problem linear, which is quite simple, but well, maybe justified. So our alpha will be a prescribed function and no back reaction. In most of the models that I will present, alpha is antisymmetric with respect to the equator, so it's proportional to cosine theta, which is justified because of elementary symmetry reason for the flow. And the ansatz B times e to gamma t leads to a linear eigenvalue problem, which is solved numerically, and delivers eigenvalues gamma, which are in general complex. So we have a growth rate sigma and an imaginary part which describes the frequency. So the first model is very simple. It's a constant alpha times cosine theta. It should be very well known. This figure shows the real part of the growth rate, which is a complete eigenvalue because all eigenvalues are real, so we have stationary solutions. And here the growth rates for I think it's the 7 simplest modes are shown. So we have critical value for alpha, and there's no coupling between symmetric and antisymmetric modes with respect to the equator. And this can be seen that we have here a degeneration between such modes. I will show this on the next slide. We have an exact degeneration for alpha equal to 0 for the free decay case. And I will also show some figures on the next slide. So if we classify our dynamo eigenmodes by the free decay modes, we end up at this picture. This is for alpha equal 0, so the free decay. We have here the poloidal dipole that is belongs to the first eigenmode with the lowest decay rate. The second mode is an L equal 1 toroidal field. The third mode is a quadrupole. The fourth mode is again a pure toroidal field. The reason for that is that toroidal and poloidal field. So I only regard axisymmetric modes, I should mention here. That they decouple for the free decay case. So there's no mechanism that couples toroidal and poloidal fields for free decay. The third mode is the fifth mode is an octopole. The sixth mode is a dipole with a higher radial wave number. And then we have again a pure toroidal field with multipolar wave number sweep. And we have some degeneration, which is shown by these arrows here. So these modes are perfectly degenerated. These modes are degenerated, and these modes here are degenerated. They have the same decay rate. This degeneration changes if I go to a higher value of alpha. This is for alpha 15. It's a growing regime. This is how the eigenfunctions of the dynamo operator looks like. And we have This is how this dipolar mode develops. This is how this toroidal, purely toroidal mode develops, and so on. And then we have a degeneration between these two modes, between these two modes, and so on. It's again shown by this node. This degeneration of symmetric and antisymmetric modes is long been known analytically for infinite models, so where we have no boundary, but it's approximately also present in these models where I have an outer boundary which is insulating. And we also see that the geometry of the degenerate modes is always pretty similar, except that the symmetry behavior is opposite. So this slide shows some results from simulations of rotating magnetoconvection, and during my PhD thesis I've tried to compute some alpha effect which should be suitable for geodynamo models. And what we see here is some alpha and the kinetic helicity. We see that this well-known relation between alpha and the negative helicity is at least qualitatively fulfilled. And we also see that the alpha is negative in the lower part of the shell, and it's positive in the upper part. So that's the assumption that alpha is negative in the northern hemisphere and positive in the other hemisphere might be too simplistic. So this leads to an alpha model for geodynamometry where some radial sign profile is prescribed. The alpha effect then looks like it's shown in this figure here. So we have a maximum at the poles. The alpha effect vanishes at the equator due to this cosine theta behavior, and we have this sign change in radial direction. We also use at the beginning a uniform diffusivity, and so applying this alpha profile in an alpha square dynamo model, we become oscillating modes around the dynamo threshold, which is shown in this spectrum. Also, the spectrum becomes much more complicated. We have interacting modes, and so I just wanted to filter out these higher modes because they are not so important for the following. So we only look at the most simple modes here. Dashed lines are indicating oscillating modes, solid lines are stationary modes. And we have here 3 points, which are so-called exceptional points, where we have a merging of 2 stationary modes, and they continue as one oscillating mode with 2 eigenvalues which are conjugate complex. So they have the same real part, the same growth rate, but they have negative and positive frequency. We have also degeneration. So we have here one single stationary mode. We have here two oscillating modes. Here another 2 oscillating modes. Here during this range we have four modes which have nearly the same real part, the same growth rate. And if we increase alpha to higher values, we have again stationary modes. We have 2 modes here and the 2 modes on the second branch. This figure shows the corresponding frequencies here, but only the positive branch. So the green color corresponds to these modes, the red color to this mode here, and blue corresponds to this mode, and this mode only shows oscillating behavior here. And for too large alpha, again, all modes are stationary. So on the next slide, I will try to examine the geometry, or which modes in the sense of 3 decay modes are involved in this reversal. So I will decompose the dynamo eigenfunction again into 3 decay modes, and this is done only for the for this stationary mode and for this oscillatory mode. And we see again, here we have the stationary range of alpha, here there's the oscillatory branch, here it's stationary again. And here the dashed curve shows 3 decay modes with higher radial wave number, and the solid curves show 3 decay modes with the radial wave number 0. So what we see here is that during the oscillatory part of the dynamo, we have a domination of modes with a higher radial wave number, and in the stationary part we have always a domination of modes with a wave number 0. The same occurs for the second oscillatory mode. We have here this part is oscillatory, it becomes stationary for increasing alpha. Again, during the oscillatory part of the dynamo, we have dominating modes with radial wave number 1. So it's essential. It seems essential that a higher radial wave number is really involved during the reversal or during the oscillating part. And for large alpha, we have a domination of higher multipolar order, and I could increase in principle the alpha for very large values, and multipolar wave number will increase and increase forever. This figure shows the effect if I introduce some finite inner core conductivity, which is higher than the conductivity of the fluid. So I've computed 4 different cases with different relation between diffusivity in the core and diffusivity in the fluid. And we see that this oscillatory branch, where the dynamo becomes growing, is hardly affected by that. The main thing that we see is that the inner core conductivity leads to a vanishing degeneration for small alphas. So this oscillatory branch here is decomposed into 2 stationary branches, and finally there is a merging of these 2 branches to some oscillatory mode, which occurs later and later with increasing conductivity of the inner core. This slide here shows the effect if I introduce some additional equatorial antisymmetry. So I added into an additional term which breaks the antisymmetry of alpha with respect to the equator, but I kept these terms small. And we see here some details from the growth rates that I presented before for alpha between 13 and 17. Here we see the oscillatory mode, which goes through and is nearly not affected at all by this equatorial symmetry breaking, whereas here these exceptional point where I have 2 stationary modes merging, this is shifted more and more to higher values of alpha, and in the end we have here 2 modes crossing, which do not and they do not interact at all anymore. But I should also mention, if I introduce such a symmetry breaking, I pretty soon end up in oscillating hemispherical models, at least during this part where I'm close to the dynamo threshold. The solution is an oscillating hemispherical dynamo, which is a result of the close behavior of dipole and quadrupole part, which is showed in the initial part of the talk. So both growth rates are pretty close, and if I add dipole, quadrupole, of course the result is, and as they have similar magnitudes, the result is a hemispherical dynamo. This figure shows some sketch of the process as we believe it occurs in nonlinear dynamos if we include alpha quenching as a back reaction of the field. Such typical behavior has been observed in one-dimensional nonlinear models of reversing alpha square dynamos, as shown by my colleague Frank Stefani, and should present a qualitative picture of the behavior during this during a reversal. So if we have a dynamo here close to the threshold, it which is stationary and is subject to some noise. We may have some noise-triggered jump to this part in the spectrum, and this fixed point is unstable, so a slight increase of alpha leads to a decaying field. Reduced quenching of alpha increases more and more, and so we have a self-accelerating decay of the field, and the dynamo is driven to this oscillatory, to this exceptional point where it becomes oscillatory. Then growth can occur again, and the quenching is increased again, and so the whole dynamo configuration can end up here again at a stable fixed point. It becomes stationary again. Essential for such a mechanism is a local maximum in the growth rate, and which should be positive here and negative here. So this is and together with noise, this is the only two things which are necessary to describe some irregular reversing. And we believe that, we believe that such a mechanism can also be obtained in the two-dimensional spherical model that I presented before, even if we don't have some exceptional point or some merging of other stationary modes to oscillate. The scenario shown in this figure here, for example, exactly gives such a mechanism if one is able to shift that close to the dynamo threshold. We have some negative slope here. We have at least small local maximum, and we have a proximity of an oscillating and stationary state, even if there is no immediate connection with this mode. So to conclude my talk, so we find oscillating solutions for a certain type of radial alpha profile, but we also know that this alpha profile must be, or that the presence of dominating oscillating solutions is very sensitive to the special radial dependence. So if you have an alpha profile, a radial alpha profile which is slightly different, then the dominating solution again is stationary. Essential for the occurrence of oscillating solutions is the occurrence of higher radial modes, and there are more than two modes involved in a reversal. So probably these very simple models which only include two different modes are too simplistic. My model, the growing oscillating solutions exist independent of chord conductivity and equatorial symmetry breaking, at least in the range that I examine. But for these equatorial symmetry breaking models, I easily end up in hemispherical dynamo action. So to apply such models for Earth-like or for geodynamo-like behavior, one must include something which leads to a vanishing of the degeneration of dipole and quadrupole part of the field. Here I restricted myself to axisymmetric modes, but there are hints in the observations that I show at the beginning that there is a higher non-axisymmetric mode involved during a reversal. So it seems that the dominating mode is an m=2 mode during a reversal from these paleomagnetic observations. And it is also known that if we apply an anisotropic alpha effect, as it should occur in a fast rotating body, then that's a non-axisymmetric, the equatorial dipole is dominating. This might be avoided if one also includes some anisotropic beta effect, which should be the case. When alpha is anisotropic, beta should be anisotropic as well. And this could again lead to a domination of the axisymmetric dipole, but this had to be examined. So future application of such models should be the examination of the spectrum for instantaneous. That means for quenched alpha distributions as they are obtained from nonlinear simulation. So I'm at the end. Thank you.
Thank you very much. Are there any questions? Yes, Alfio.
Sorry, because I was a bit late. Can you talk about the boundary conditions? So which boundary condition do you use for the inner part?
For the inner part, there are no boundary conditions because there's only regular behavior at the center of the sphere.
No, but I mean,
Which is conducting, yes.
You must have either a perfect conductor or...
No. In principle...
So, okay, let's change the question this way. Suppose you have an inner annulus, something like finite, okay, like 1/10 of the solar radius.
In principle,
How is your result dependent on the possible boundary condition you will choose at the inner part?
No, the inner boundary condition is just I demand regular behavior. There is no need for an inner boundary condition.
Regular behavior means that the vector potential goes to 0 and everything goes to 0. What do you mean?
No. I decompose the magnetic field into a poloidal and toroidal eigenfunctions, and then for my numerical method I use the expansion in 3 decay modes.
Okay,
so they are analytical known, and so there is no need. The outer boundary is an insulator, and this behavior is also known. So these analytical solutions, they fulfill the necessary boundary conditions at the center of the sphere and at the outer boundary. So there are no special boundary conditions.
So okay. So if you haven't tried to consider a finite inner part in the core. You have not tried to
no, the inner core is present, but it has, and I can describe the conductivity as I want. I can show you maybe.
Thank you.
One more question by another question I have here. You showed at the beginning alpha profiles as a function of radius, and you had basically a sinusoidal profile. Could one not equally well, or even better, expect that alpha, as the sketch almost indicates here, is actually peaked towards the boundaries? And this you did not actually believe, I guess, as you find on the right-hand side. And it should be much more extreme as the Reynolds number goes up. Or the
yes, when I increase my rotation in this box, these peaks become closer to the boundary, and it seems that the alpha is more a boundary effect.
You should maybe then accept that and use that in the models.
Yes, of course, but so this model is quite simple and leads to oscillating solutions. So I don't know what happens if I restrict alpha to some shells or to some very tiny shells with a delta function. I don't know. I could do that.
A related question: how did you actually measure alpha?
This is very simple. I applied a magnetic field in horizontal direction and computed in full 3D MHD simulations. I computed the electromotive force, and then I computed alpha. The more elaborate way would be a test field method, but at that time I didn't use that test field. So this is, I do not claim that this result may be realized in the Earth, but it should just be a motivation why I use this sign profile. So these models in a box, they don't consider curvature, they don't consider some tangent cylinder, which might also be important. So just a motivation for this sign profile, that's all.
Right. Okay, thank you very much.
If I speak without microphone, it would be okay.
Yeah,
I've noticed that your two-dimensional model has no regard of axisymmetry or phi, obviously. And at the same time, you know that lots of alpha square, simple alpha square models, for example, asymptotic studies show that alpha square omega have preference for non-axisymmetric versus azimuth phi modes, the generation of those modes. Sometimes more preferable and has lower critical thresholds. Have you ever considered to study such extension of your approach?
So for this model that I present here, the axisymmetric mode has the highest growth rate. But if I would apply some anisotropic alpha effect, then the non-axisymmetric mode will be dominant. But I only apply the isotropic alpha.
Mm-hmm. But you've done this study. But you have studied non-axisymmetric modes as well.
Yes, with anisotropic alpha effect, the dominating modes will be non-axisymmetric. But in this models, always the dominating modes are always axisymmetric.
Okay. So thanks again, and we move on with the next talk by Ruba Mitra, also about after square dynamos and oscillations of them.
So I'm going to talk about oscillatory migrating magnetic fields in spherical domain. The motivation is actually the solar dynamo, although we will actually see how much this has got to do something with the solar dynamo. The different parts of the work has been done with different people, and actually 4 of my collaborators are there in this room now, which is a happy occurrence for me. They can correct me if I am saying anything stupid. So I had expected that almost every other talk in this meeting will actually show this plot, but they haven't, so let me. So this is the butterfly diagram of the solar magnetic field, which is, I guess, pretty well known to everybody. There are features here that are of particular interest to us. So one is that there are oscillations and polarity reversal, which is the 22-year solar cycle. There is the equatorward migration of the sunspot. There is also a poleward migration of the diffusing field. Also, we note that the azimuthally averaged field is rather weak compared to the peak field at the sunspots. But we also know that how the profile of angular velocity looks in the sun from heliosismology studies. So we know that there is a strong shear sitting at the bottom of the convection zone, which is the Tacoth line. And we also know that there is a near surface shear layer. But over here, in this region, we know how d omega dr, where omega is the angular velocity, looks like. So, and we also expect that the alpha effect is actually positive in the northern hemisphere. So if one looks at the product of alpha and the d omega dr one would find here, one would expect that from the Parker-Yoshimura sum rule, the migration rule, that it should actually migrate towards the pole. Although we know that the sunspot migrates towards the equator. Now let me just touch about what we dynamo simulators would actually like to do. Now we would like to have a model which incorporates all the essential ingredients: rotation, convection, differential rotation. And we would like to do it in big sizes. We would like to find large-scale magnetic fields. And this large-scale magnetic field then should show spatiotemporal behavior similar to the sun. In particular, it should show oscillations and equatorward migrations. And the dynamics should persist even at very high Reynolds number. That's also an important feature, that we should actually see equipartition magnetic field at very high Reynolds numbers. Now, as it turns out, the reality is, as present from our simulations, is quite different. What we have is, we have done simulations in full sphere. Several groups have done this, sometime in full sphere, sometime like us in parts of sphere. We have rotation, we have convection, but we are not really there. There are Cartesian simulations of force turbulence, which has shown large-scale magnetic fields. There are Cartesian simulations in shear and convection, which has also shown large-scale magnetic field. These are the famous simulations by Petri Kapila, and also somewhat slightly later the same simulations were done by David Hughes and Mike Proctor. But the spherical convection simulations, which has been done by several groups now, by Brun and Misch, the NCAR group, by us, and also by, I think, Charbonneu's group, and none of these actually show what we want. It does show large-scale magnetic field, but if there are migrations at all, the migrations are always poleward. So this is where we are stuck now, actually. And actually, it may be that that's not exactly where we are stuck, because the angular velocity profile that we obtain from our simulations are also not solar-like. So maybe we are stuck somewhere else, but somehow we are not there. So what we have done is to actually propose a minimal model which shows solar-like behavior. So the idea is simple, is to solve compressible MHD in a sphere, but not in a full sphere. It's a spherical wedge. So U is the velocity. We have the usual Lorentz force, the viscous terms, the usual induction equation. The interesting parts comes from this F, which is an external force. So we don't have convection, we don't have rotation, but we have some spirit of those in a helical external force. And the helicity is actually negative in the northern hemisphere and positive in the southern hemisphere. When we started doing the simulations in spherical domains, such forcing we presume should be constructed out of what are known as Chandrasekhar-Kendall functions. So which are a combination of Bessel's functions and spherical harmonics. Very nice, mathematically very nice quantities. So we spent some time doing them. And later it turned out that we actually don't need such a complicated forcing. It's actually a simple sine-cosine forcing in the spherical coordinates which does the job. So the main ingredient is to have a forcing which has two hemispheres, an external force which injects negative helicity in the north and positive in the south. This is kind of supposed to mimic the effect of rotation and stratification, and there is no differential rotation or large-scale shear in our problem. We do see large-scale magnetic field. As you see, this is basically the wedge I am talking about. The gaps are not simulated. There is a periodic boundary condition along the azimuthal direction. The radial boundary conditions are perfect conductor. So are the boundary conditions at the top and at the bottom. So this is what we obtain from our simulations. So the first thing first, this is the DNS, and this is kind of the sketch of the meridional plane where we are doing our simulations. You can see that we have polarity reversal, we have equator-ward migration. Then we did our DNS with the domain, which is half the domain, but an antisymmetric boundary condition for the magnetic field imposed at the equator. And that reproduces half the butterfly diagram pretty well. And next we went about doing the same thing in mean field with a simple alpha squared dynamo and with again another antisymmetric boundary condition at the equator, and that reproduces essentially the same behavior. So the question, there are now several questions that one must ask. So one is, what happens to this frequency of oscillations as we look at higher and higher magnetic Reynolds numbers? So in the inset, I am plotting the frequency of the oscillations from the direct numerical simulations as a function of magnetic Reynolds number. As you can see, the range of Reynolds numbers is pitifully little, but you know that in DNS we can't do much better. It's roughly a constant. Then we kind of normalize them by what we presume should be an estimate of the frequency of the oscillations. The time scales we are presuming will be some turbulent diffusivity eta t multiplied by the typical wave number along the theta direction. So this is the time, but we normalize it by. These points are the same points here, and the other points are from the mean field simulations, where you can of course go to much larger magnetic Reynolds number. So you see the range over which frequency changes is actually very little. So it's not that the oscillations are slowing down as we are going to higher Reynolds number or anything like that. The oscillations will persist, and the same behavior of equator-ward migration will also persist. This is the phase relation between the energy in the toroidal and the poloidal magnetic field. They're actually slightly out of phase, and then we go over to actually write down the mean field model. So this is the usual mean field model of the alpha squared dynamo. The second equation is the dynamical alpha quenching equation. The alpha has two parts, the kinetic part and the magnetic part. And it's the magnetic part which actually changes in time, the kinetic part being a constant. So this model is the one that has actually given us the oscillations on the equator about migration that we have shown. When we first saw these results in our DNAs, we were somewhat surprised. We were not actually expecting oscillatory behavior in alpha squared dynamo. But as it turned out, this problem is known from long back. And the reason I am presenting it particularly in this meeting is that one of the first people to work on this is actually Karl-Heinz. So this goes back to 1987. There are two accompanying papers in the same issue of Astronomical Notes. There is this paper by Barashnikova and Shukurov which looks at oscillatory alpha squared dynamos. Their main motivation was actually galactic dynamos. It was a 1D model. And there is this work of Karl-Heinz and Brouwer, where they're looking at oscillatory behavior of kinematic midfield dynamos. This is the earliest paper that I know, which looked at what happens when the sign of alpha changes across the equator. There were other issues that are considered in this paper. For example, in this paper, he considers what happens when you have non-axis symmetric fields, and there he sees dynamo waves propagating along the azimuth. But for axisymmetric fields, and antisymmetric alpha actually gives you the behavior that we are seeing. The thing that was missing, the only thing that was missing in this paper, was that the direction of migration was not investigated. So that's kind of what our input from the direct numerical simulations. The other question that one should ask in such problems is that what happens to the magnetic field or the magnetic energy as we go to higher and higher magnetic Reynolds number. So this is the well-known alpha quenching problem. So the lower plot here, so of course in DNS we can't go to much higher Reynolds number, so now we are in the mean field regime. So the lower plot here is the magnetic energy as a function of magnetic Reynolds number for this model. And one can see that there is roughly a 1 over Rm scaling for these magnetic energies. Such a quenching, this is a behavior which is known as alpha quenching, and such quenching can be alleviated by actually incorporating a wind in the equation for the magnetic alpha effect. This is exactly what Anwar was talking about yesterday. He was talking about galactic winds. Here we have included a solar wind, and that is again able to remove the quenching and give us a reasonable magnetic field even at very high magnetic Reynolds number. So let's see. So one of the things is that the frequency of the oscillations are not resistively limited. So we are expecting that at very high Reynolds number the behavior will persist. But the initial growth phase there is an initial growth phase which becomes longer as you go to higher and higher magnetic Reynolds number. The magnetic field in the mean field simulations are catastrophically quenched, but this may be alleviated by diffusive flux of magnetic helicity across the equator. Just in the previous slide, I was talking about advective flux due to a wind, but there is also the possibility of diffusive flux of magnetic helicity across the equator, which is another question I will look at in a couple of slides later. So presumably simulations with stratification and rigid rotation will reproduce the same results, but we need much higher resolutions. So there are more questions that remain. So in the absence of any other mechanism, magnetic helicity is transported across the equator by diffusion. So the question is, for such a diffusion, can one define a diffusion coefficient? And when one gets such a diffusion coefficient, will that be a diffusion coefficient which is of the same order as the turbulent diffusivity, or the same order as the molecular diffusivity? So that's the question we will look at a little bit later. The question of including convection and rigid rotation is something we haven't been able to do yet. How will differential rotation, inclusion of differential rotation, change all this? That's something we have investigated, at least in mean field models. If you have a solar rotation profile, and now of course I have the freedom of choosing alpha and omega as I want. For weak omega, the alpha squared dynamo is the dominant one, and we see the behavior I have been saying here. For a strong enough omega, one actually can see poleward migration of the magnetic activity. And then how will the picture change as we go close to the pole? In all these simulations, we have actually not included the pole. The mean field simulations where we have been able to go quite close to the pole suggest that basically nothing will change. So let me just touch a bit on the transport of magnetic helicity across the equator. But here we have tested it for an even simpler problem. So we have replaced the sphere by a Cartesian box, but the spirit of the forcing is the same. It gives one sign of helicity in the north and another sign of helicity in the south. And then our aim is to look at these equations which describes the evolution of the magnetic helicity. The interesting point here is the last term in the equation which describes the divergence of a helicity flux. So we are trying to model this flux in terms of a diffusion, and here is the diffusion coefficient, the kappa f, that is of interest to us. From simulations at various Reynolds numbers, ranging up to something about 50 if I remember it correctly, we actually get a ratio of something like this between the kappa and the turbulent magnetic diffusivity. And so this ratio says this is roughly a constant. So this supports the fact, well, may not be a fact as proven yet. This supports at least our conjecture that the diffusion coefficients that one can define for such a magnetic helicity flux is of the same order as the turbulent magnetic diffusivity. But of course note that our the ratio between turbulent magnetic diffusivity and the molecular diffusivity is not a big one in our simulations because these are DNS at moderate Reynolds numbers. Okay, that's the end of it. Thank you.
Thank you very much, Ruben. Is there any questions? No questions, really. Axel.
That maybe is a question to Karl-Heinz and perhaps others who were involved at the time. What did you think when you found oscillatory dynamo action? Did you think this was of any use at the time, or do you think that was somehow just a curiosity and of no interest?
I was not sure that I was not sure that it was of any use, but it was just a question. All what was observed at the alpha square dynamo was monitored in time. No oscillation. And is it a basic law? Can an alpha square dynamo have no oscillation or not? This was the motivation for this question. But I mean, considering this problem.
And everybody else forgot about it again. Until
Well, no, yeah, I just want to be in the nonlinear zoo, one has everything in its opposite. I mean, it's as soon as you penetrate the zoo of possible bifurcations, etc., expect anything.
yes. But I mean, here we are still in the linear regime.
Yeah, that's even the linear regime. When you look at the question of bifurcation of eigenvalues, you have also. This is quite generic.
That things become oscillatory, yeah?
Yeah.
Right. I remember the same thing with the Hertzog dynamo, but I'm not sure I should tell such a joke here. At this time, right? The joke is, of course, that the Hertzog dynamo was run for an angle of between 0 and 90 degrees when there should be no dynamo action. And that was exactly the case when the experiment was done. And it was found that it was oscillatory. And Fritz Krause said, yeah, but this is not surprising because it should be nonlinear. And only later with Andrew and with David Moss, we found that there are indeed linear solutions in exactly the regime where the Hertzog dynamo, according to the original Hertzog paper, was not supposed to work. And it was just linear theory, which was overlooked because people thought of the diffusion length as opposed to the spin depth as a relevant length scale and ignored the possibility of time-dependent solutions.
Didn't Guy Elitis find that too?
Say again?
Didn't Guy Elitis find oscillatory? Didn't Guy Elitis find oscillatory dynamos in their orientation, didn't he?
In that regime, I'm not sure now. Andrew, do you remember?
Well, I know you got oscillatory dynamos, but I don't know about which regime it was.
Yes.
They certainly got the oscillatory modes.
And I remember that one too.
I'm
yes.
sure we referred to that too.
Yeah, that's a different one.
I mean,
But
just one more word. No, there's no need to bring the microphone. I mean, the induction operator is neither Hermitian nor anti-Hermitian. It is a rather generic operator. It is not quite as vicious as the operator one encounters when linearizing ordinary hydrodynamics or Sommerfeld thing. But it's getting there, so just expect anything.
Yes. In fact, this was exactly the motivation for our work in this. It was 1985, I think, Magenta hydrodynamics, that the operator of alpha squared isn't self-adjoint. Therefore, you should expect oscillatory solutions. Meanwhile, all numerical solutions were steady, and then we applied a WKB solution to the alpha squared dynamo, and then just conjectured at the end of the paper that at higher orders, the first two orders, the eigenvalues were real, and then it was my first talk at international conference when I was just a PhD student, just finished my PhD, when I made this statement that there must be oscillations because of the reason you point out. And then you can imagine my horror when Karl-Heinz stood up and said that no way, it must be, must be an oscillatory. But then first it forced us to get fourth order expansion in the fourth order in WKB. The eigenvalue became complex, but in this paper, in astrometry, it's another type of oscillations. There is another type of oscillations in alpha squared which arise from boundary conditions, not from the non-self-adjointness of the operator, but from boundary conditions. And the period of these oscillations is much shorter than the one which comes from. So it's a rich system. There can be oscillations of different types. Some coming from the bulk of the dynamo region, from the nature of the operator. The others from boundary effects. We couldn't quite understand the nature of these boundary effects, I should admit. But the frequency was entirely different from what you get from the operator itself.
Let me just take this chance to ask a question. So this is the paper, I think, which both Karl-Heinz's paper and Anwar's paper refer back to as the first paper which actually considers oscillatory solutions for alpha squared.
No, it is the fourth order expansion in our alpha.
Now the question is, I couldn't find this paper. As two-thirds of the authors are here, do you have a copy of this?
In Russian.
Yes, but I couldn't get English.
You can if you pay money to Magenta hydrodynamics now.
But Dmitry is a member, is on the editorial board of Magenta hydrodynamics. So do you have access to their website? Can you download this paper from their website?
Pay money.
I'm not sure it's from here, but
well, I spent several hours trying to dig it out yesterday and the day before.
We should stick to the scientific problems more. Frank.
Maybe one remark. I think in the last years it has turned out that there is a nice similarity of the dynamo operator with BT symmetric quantum mechanics. And it's very convenient to go over from Hilbert space to Krein space with the indefinite metric. And then you have the poloidal toroidal structure, gives you a very natural structure which you can describe in the Krein space. And then all those things that you get exceptional points and oscillatory solutions are very, very natural in this setup. I think it has to be noted what has been done in the last years in this field.
All right, thank you. Thank you, Gruber, again. And we move on with Martin Schrinner, talking about oscillatory dynamos, in this case, direct simulations, I suppose.
Some technical problems. morning, everybody. I'm going to present also work on oscillatory dynamo models. Collaborators are Ludovic Petit-Demange and Emmanuel Domi. As you already heard, the best known example among oscillatory dynamos is of course a solar dynamo. Shown in this chart is the average daily sunspot area in percent of the visible hemisphere varying in time. The activity cycle is irregular, but as we all know, there is a rather well-defined period length of 11 years. There are also a number of other stars claimed at least to show cyclic activity. Here the period lengths vary from 2 to 25 years. But of course, by far, not all stars or all stellar dynamos are oscillatory, hence there is a fundamental problem or a fundamental question: why are some stellar dynamos oscillatory or others not? In order to tackle this problem, we look at convective dynamo models. These models are solutions of the MHD equations for a conducting Kuznets fluid in a rotating spherical shell. Convection is driven by an imposed temperature gradient between the inner and the outer boundary. Let me define for later use the aspect ratio as the radius of the inner sphere divided by the radius of the outer sphere. Of course, these models are unrealistic. For example, they do not include compressibility, and they will run in the wrong parameter regime. But probably none of these realistic conditions alone is responsible for the huge variety of stellar magnetic fields, because all stellar dynamos share them. A brief look at the equations in Kuznets approximation. We already have seen this. We solve the momentum equation, the temperature equation, and the induction equation. In this non-dimensional form, the system is governed by 4 parameters. These are the Ekman number, the Rayleigh number, the Prandtl number, and the magnetic Prandtl number. And in addition, as already mentioned, but not visible here in this equation, there's also the aspect ratio of the shell. Dynamo waves are present in simulations with stress-free mechanical boundary conditions. These simulations exhibit a strong field branch and a weak field branch, depending on the initial conditions of a magnetic field. If a magnetic field is initially weak, stress-free mechanical boundary conditions enable the development of a strong zonal flow carrying most of the kinetic energy. The magnetic field resulting from these dynamos is small-scaled, often of quadrupolar symmetry, and weak. The transition from steady to oscillatory dynamos may also be governed by the width of a convection zone. Goddard and Domi found oscillatory models by decreasing the shell width. This experiment is extremely appealing because it explains the difference between the Earth's magnetic field and the solar magnetic field in a very simple way at least at first glance. This slide introduces the model under consideration. We are looking at the radial velocity field at a certain radial level. The magnetic Reynolds number is about 80, thus rather low when the dynamo is close to onset. The mechanical boundary conditions have been chosen to be rigid at the inner boundary and stress-free at the outer boundary. Of particular interest is the relatively high aspect ratio of 0.65. Models with these parameters become oscillatory if the aspect ratio is increased up to this value. The oscillatory nature of this example is most clearly visible in a typical butterfly diagram. Here we are looking at the azimuthally averaged radial magnetic field at the outer spherical shell, depending still on colatitude and varying with time. A dynamo wave is migrating away from the equator. Just a brief remark, we already heard a lot about this and we discussed it. But sometimes it's stated that oscillatory models and steady dynamos may be distinguished by their dynamo mechanism. For this model, this is not the case. So the reason why here we have a cyclic time dependence. It's not due to a particular dynamo mechanism. You find more details in a recently submitted manuscript, which is available in the archive. So let's go back to the model under consideration and have a look at the dynamo in some more detail. The magnetic field is small-scaled or multipolar. This was already apparent in the last view graph and is confirmed by the spectral magnetic energy distribution. We consider here magnetic energy as a function of harmonic degree L, summing over m and averaging over radius and in time. Very typical for these kind of magnetic field configurations, the spectrum is essentially white, with the exception of a particularly low dipole contribution. Note that we did not truncate the model at this value, but only at an L max of 128. The magnetic field is not only small-scale or multipolar, it is also comparatively weak. The kinetic energy density exceeds the magnetic one by an order of magnitude. In order to explain another property of oscillatory, typical property of oscillatory dynamos, I have to introduce the concept of kinematic stability. So if we solve the MHD equations together with the second induction equation, which describes the evolution of passive vector field or tracer field in general, this tracer field will grow exponentially in time. Note that there is an important class of dynamo models which are kinematically stable in the sense, which is explained in this paper. But unfortunately, oscillatory dynamos do not belong to this dynamo class. So let me summarize the mentioned properties of our thin shell model so far. The magnetic field is multipolar and weak. It shows cyclic time dependence, and kinematically advanced tracer field grows exponentially in time. In contrast, models with these parameters but a smaller aspect ratio have a dipolar magnetic field. The magnetic field is strong, the dipole field is stable, and these models are also kinematically stable. These two dynamo regimes presented here are very similar to those already established by Christensen and Aubert in 2006, and indeed will turn out that they are identical and can be more generally determined by the Rossby number. The Rossby number, we have seen already, is defined here in a very conventional way, where there's a velocity amplitude over a typical length scale and angular velocity. But more precisely, I do refer here to a so-called local Rossby number or weighted Rossby number, which is based on a length scale derived from the kinetic energy spectrum of a flow. I follow here Christensen and Aubert. What's plotted here? Here, the relative dipole field strength at the outer shell is plotted for various models versus the local Rossby number. Let's consider first only the black symbols. Black stars denote dipole-dominated models with a stable dipole field at low Rossby number. Black triangles stand for multipolar models at higher Rossby number, which exhibit reversals and a very irregular time dependence. The oscillatory model we considered is denoted by this red triangle here. It belongs to the multipolar dynamo regime. The red stars are models which differ from the oscillatory model only by a smaller aspect ratio. They belong to the dipolar dynamo regime. The transition between both regimes occurs roughly at a Rossby number of 0.1. Apparently, our oscillatory, the model we consider is oscillatory because its Rossby number is larger than 0.1. Of course, there is a problem that not all high Rossby number dynamos show coherent cyclic time dependence. So let's have maybe a closer look to both dynamo regimes. Dipolar models in the low Rossby number regime are dominated by only one fundamental dynamo mode. more spatially structured overtones are diffusive, while the fundamental mode at time average has zero growth rate. Small-scale contributions to a magnetic field result from the deformation of this fundamental mode, and subsequently they decay due to ohmic diffusion. Approaching now the regime boundary, the dipolar fundamental mode becomes less dominant, and we will find alternating growth of many modes finally in multipolar dynamo regime. This is illustrated by this view graph. Here I plotted the growth rates of the fundamental mode triangles and the growth rates of the first following dipolar overtone as stars for 4 models with different Rossby number. For this model at low Rossby number, there's a huge gap between the fundamental mode and the first following overtone, while both growth rates are much closer at higher Rossby number, if the Rossby number increases. I have really problems with this microphone. I should maybe do not use it. Okay. Another illustration of this argument is provided by a comparison of models at both sides of a regime boundary. The counterplots here give real parts of a radial component of eigenmodes for a dipolar model and an oscillatory model. The dipolar model at slightly lower growth rate is governed by the dipolar eigenmode, the real dipolar eigenmode at zero growth rate, while the following overtones, oscillatory overtones, are damped. This model differs from the oscillatory model in an inversed order of eigenmodes. If the convection columns are perturbed and due to smaller convective length scales, more structured overtones become preferred, these overtones are very likely to be complex and thus very naturally lead to a cyclic time dependence. However, if too many of them become eventually supercritical, one has to expect that coherent time dependence gets lost. This seems to be indeed the case if we force the dipolar model at aspect ratio here 0.6 if we force the transition of this dipolar model to the multipolar regime by increasing, for example, the radial number, we also end up with a higher magnetic Reynolds number. And as a consequence, we see that the resultant butterfly diagram is already much less coherent. So, to summarize, we do find oscillatory dynamo models in the high Rossby number regime, but only for moderate or low magnetic Reynolds number. Of course, this dynamo regime is not compatible with conditions in the solar convection zone, and present or these dynamo simulations are really in conflict with the idea of a coherent magnetic field generated in the turbulent solar convection zone. My conclusions: oscillatory dynamos in these simulations are multipower dynamos close to critical conditions. The transition towards the oscillatory regime is caused by an increase of the Rossby number, which can be performed, for example, by decreasing the length scale. And this dynamo regime is not compatible with conditions in the solar convection zone. Before I come to the end, a last view graph. I have to explain why I've chosen this picture. First, there are basically two reasons. First, I feel a little bit as being a delegate of the Göttingen Dynamo community here. So this is a picture of Göttingen. And you see a fountain, and this fountain you find a figure or a statue which represents the figure of a famous German fairy tale. So this is Göttingen. I said this. There's another reason why I've chosen this. So I feel a little bit as one of your last PhD students, although this is officially not true, but we had a very intensive collaboration, and you helped me a lot during my PhD time. And after having received your PhD in Göttingen, all PhD students, in a sense, have to climb this fountain and have to kiss this statue. So I guess this is the most kissed girl in Göttingen. This man eventually looks like this. So Karl-Heinz, thank you very much for everything you taught us.
Thank you, Martin. Kind words.
Thank you very much, Martin, for the nice talk. Are there any questions? None. Everybody disappointed by not being applicable to the sun? All right, maybe questions come up anyway. Yeah.
There was one thing which I there was Axel made some comparisons of stellar magnetic fields scaling to the Rossby numbers, right? Is there any agreement or connection with that? Because obviously it's an important parameter, Rossby number, and Axel did quite a lot of work on comparing observations with Rossby, and also Dmitry did a lot.
Yes. So the Rossby number is here indeed a very important parameter which distinguishes two dynamo regimes. I know from stellar observations that people say people observe a saturation also of field strength with Rossby number, but before they see also an increase of magnetic field strength with Rossby number. This is not evident simply in these simulations. So it's not. It's maybe not that. I do not see at the moment this increase of magnetic field strength with Rossby number. There's a very sharp transition. This is clear. Absolutely.
But this is very interesting, right? So that you know what to do.
Yes.
Or where to go. Yes.
Well, specifically, it was not actually so much the field strength as the ratio of the oscillatory frequency to the rotational frequency as a function of Rossby number. And that is something that people like Béranger, de Bruyne, and I think you were involved in this, Frank, maybe? Or some other people in France at least, around Béranger. They used it for the Carrerage experiment, because in the Carrerage experiment you can also get oscillatory solutions as a function of, if you have the rotor rates of the two propellers different from each other, then you can calculate from that something like a angular velocity, or something which corresponds to angular velocity. And so the ratio then between the oscillatory frequency and that angular velocity is inversely proportional to the Rossby number, or to the inverse Rossby number, so the Curie's number. And so in that actually, for reasons that may not be real, agreed with what we find for stellar dynamos, oscillatory stellar dynamos, over a vast range of periods. So if you have your oscillatories, if you have your oscillations, you can maybe also put that onto this diagram. We found three different branches, and we are here talking about the hyperactive branches. We had inactive, where the sun lies. We have an active branch, where, for example, the Gleisberg cycle of the sun would lie, but also a few other stellar cycles. And then there's a hyperactive branch where a lot of extremely active stars would lie. In principle, perhaps even I shouldn't really say this, the geodynamo is maybe also, but it doesn't have a period, of course. But anyway, the Karaj experiment, for reasons that we don't know whether it really makes sense, fit on this diagram.
Okay, thank you. There's one more question, Amit, yeah?
Speaking about the interpretation of stellar activity data, one have to take into account that the direction of activity wave propagation is a matter of discussion. And if we analyze what observers are speaking about, we see that there are 2 or 3 examples in which observers take risk to determine the direction of activity wave propagation, and at least in one case, Bertunian and Henry published it, the direction of propagation is polar one. And it is just, so the situation with polar ward active dynamo waves is not so hopeless as people could think before.
Right, these are excellent things to be discussed on the Potsdam Think Shop in August, so everybody is welcome.
Definitely, I hope that we will
have some new
overcome the referee problem.
Ah, okay. I see. Right. If there are no more questions, I would like to thank Martin again and every speaker of the morning. We'll have coffee break now and come back at 11 o'clock.